Okay, it's 35, and let's begin. So today we are going to talk about foundational models for decision making. So I think it's one of the most exciting areas of research in robotics right now. Foundational models has been a buzzword for a while since ChatGPT. How many of you have tried ChatGPT? Almost everyone. Yeah, so great. So I think everybody already has some knowledge about what are we going to talk about today. However, I think what we are going to talk about today will be way more than just ChatGPT, and you will see at the end of the lecture. I prepared a lot of slides, and hopefully we could cover them all throughout the lecture. So the agenda today, we are going to talk about three major topics. So the first one is large language models and their application in embodied AI, aka robotics or like a game-playing agents. The second one is the challenges and opportunities in foundational models for decision making. Finally, I'm going to talk about vision foundation models, which fewer people are aware of. The first section is task planning with large language models. I have a subtitle here, Connect Unstructured World with Structured Algorithms. And you will see why this is the case. In everyday life, imagine that you have a general purpose robot. Imagine it's already 22nd century. What do you want your robot to do for you? You want to just say that, I spilled my drink, can you help? You want to say that I just worked out, can you bring me a snack and drink to recover? You want to give the robot free-form instructions, and you hope your robot could just help you out end to end, just from instructions, just like a human. However, we're in 21st century, we're not in 22nd century yet, and current robot algorithms are quite different from what we will have in the future. So right now, you have to specify a lot of things manually, aka structural quantities. For example, you want to everybody have done this example in some of their homeworks and in previous lectures. What do we need for a robot to pick this thing up is that you need to specify what to segment. You pick the segmented point cloud, and you plan a grasp like using the calculated surface normal. Russ also talked about finite state machines in previous lectures, which allow robots to execute a graph of tasks throughout its task execution. So these are all very structured algorithms. Every algorithm has a very structured inputs, very structured outputs. Like for example, graph planning meant taking segmentation and point cloud and output a graph pose. The thing is that if you look at the slide before, the human instructions are quite unstructured. And the core problem is, how can we connect the unstructured instructions with the structured algorithms? And that's the magic of large language models. For example, if I tell the robot to clean up the spilled Coke, I suppose large language model could give us a lot of instructions, such as you want to set the Coke can into upright position, you can find some napkins, you can pick up napkins. That's how a human do all these tasks. And humans use language as abstractions of tasks. You use languages as plans. And the question is, can we use the human priors and knowledges for our task planning? It turns out human activities on the internet produces a lot of knowledge in the form of text. For example, here is an image about how to make fried rice. And to make fried rice, this website tells you you need to scramble your eggs, you need to saute your vegetables and garlics, and so on. All these knowledges are on the internet for free. You just need to watch ads, and that's it. But they are widely available, and you have almost unlimited amount of data on internet. And for those who doesn't know what a large language model is, I know this class, many people in this class came from a very different background. So just let me briefly go through how this large language model works. So what is a language model? So imagine that your language model sees the sentence here. The students open their empty, the blank. And a large language model would give you a distribution of the next word based on the context it just saw. For example, the students open their books, laptops, exams, minds. A language model can assign a probability to every single word in the whole dictionary. For example, I say book has 40% probability. Laptops come with a 20% probability. And basically, assume each word is your X here. A language model basically models what will come next, what's the probability distribution of next word conditional on previous words, and that's a language model. And turns out like language model can like give you can evaluate the given you can also give your language model a next word and evaluate its log likelihood using the same method. So what's the highlight? That is, given a fixed list of options, one can evaluate the likelihood with language models. And given all the human vocabularies, one can sample with certain likelihood to generate like the next word. That's how like all the large language models work nowadays, including ChatGPT and GPT-3. Some you might have used it before in your homework, CIMs, I don't know. Yeah, so you actually use language models every day. When you type your English words, a language model, maybe some with not with neural network, but with primitive methods, can predict what's a likely next word and help you simplify the process. You can also use it to complete essays. If you just give it like some text prompt at the very beginning, it just recursively predict the next word and sample from the distribution I just talked about. And as a result, like when you do this sampling recursively, you will be able to get an entire essay. It could, yeah, you can, for example, like I just take some like essay homework from MIT class, and large language model is going to give me an essay. Hopefully this is correct, but it's not encouraged to use GPT for your homework. Okay, large language models can also code, because you can have a large language model just look at the context you provided, look at the code you already write. For example, the APIs, and it will be able to understand that and predict the function for you once you type in its name, because they have read so many code. They will have all this knowledge about like what people want to write next. So this is really powerful for robotics planning as well. For example, I can say that give me a list of items I will need to make a cup of coffee, and suddenly with your language model, it will be able to give you a magically give you a list of like grounded coffee beans, water, and these are really used for structured quantities for planning, as you will see later in some some papers we will present today. So in addition, you can ask it for a list of instructions. Okay, here I ask it like robotic instructions to give me a really detailed list, like with 12 steps. It says place a coffee mug on a stable surface near your coffee maker. If you're using coffee pot, place a filter in the filter basket. It's really complicated, but like it shows us that large language model capture a lot of useful knowledge we humans have, and we can use them to inform robots. So, however, how do we connect this unstructured thing to our structured algorithm? The first ingredient here is that you need to bind each executable skill to some text options. Imagine that my robot is equipped with a skill called like pick up an apple, another skill of like pick up a book, and you want to bind them to some like text options that the large language models can choose from. Second, you have a list of text options for L to choose from, and finally you give your language model your instruction. For example, say, can you bring me some fruits? And like the large language model will predict the options that like picking up an apple should be more likely than picking up a book to feed you. So this is essentially what people did in this paper. Like as a beginning, you just need to prompt your large language model. How would you put an apple on the table? Prompt it with I would, like, and the first step. Like it will just tell you the likelihood of every single option. If you give it a text, it could evaluate it. The second ingredient is that you can prompt large language models to output in a more structured way and parse the unstructured input, parse them into a structured output. For example, the big magic of language model is that they somewhat serve as a universal pattern machines, and you just need to prompt it with some logic, and it will be able to copy that logic and apply it on new data. For example, here I typed in United States, Washington, D.C., which is the capital. Burger is a representative food of this country. And finally, it's a mountain. And I give you 3 examples. And at the end, I prompted with France, a new country. And somehow, like, it's able to like copy this logic and output the information I need in a very structured way, separated by a comma. And you can imagine this is really useful because by using these examples, I was able to constrain its output to be in certain forms that I can easily parse with Python strings. So similarly, if I apply it on robotics data, I just give it a few examples. Like for example, like as a human move the water from the table to the counter, the robot will output a lot of steps like in my instruction. And then now I give it something completely new, like for example, human, bring me a banana from the banana launch. And a robot will copy the logic before and output a sequence of plants. So we are going to look at our first case study here. It's a paper from Google. In this paper, we have this problem. Large language models aren't grounded in the real world. They don't know what's actually possible from a state with a given embodiment. For example, like if I say I'm hungry, I want you to give me some fruits, and the robot is in front of the table, and turns out like it has this idea about like the action coming up, the plan that's coming up next should be, for example, like pick up an apple, pick up an orange, pick up a banana. However, it only sees an apple. There is only one apple on the table. And instead of sampling uniformly from its language priors, you also want language model to be informed of what's actually possible given the current scenario. So here, what they propose is that we combine language model with robotic affordance. For example, here, like, you guys have learned about reinforcement learning in previous lectures. In previous reinforcement learning, we have a value function that's conditional on state. So a state could also be an image observation. That is, like, for example, given the image observation of an apple right in front of you, like you can have a value function, the high value function towards a goal of picking up an apple, and you can have a really low value function against the task of picking up a banana. So that can be learned from RL. And what they propose here is that I just combine this affordance with the language model likelihood. So previously, how would you put an apple on the table? The language model would assign a bunch of probabilities to each option. And there is affordance that's conditional on image observation. You will also be able to predict the score about how likely I can achieve each of the tasks. And by summing, by taking the sum of them, these are the likelihoods, by just taking the sum is equivalent to multiplying their probability, and they will be able to get an overall likelihood for choosing the next skill. And you can see that, like here, you have a task of I spill my Coke on the table. How would you throw it away and bring me something to help clean? So the robot chooses from a set of skill libraries. For example, here it has find the Coke can, pick up the Coke can. This is a list of pre-generated skills that a robot can choose from. And here, at the very beginning, is from a random location. It decides it needs to find the Coke can first, which is the most likely outcome from the language model. The left-hand side is the language model. And then it walks to the Coke can. Then it determines that I should pick up the Coke can. I pick it up. Later on, like you realize, like actually at every single time step, it will have an option called down, right? And sometimes you don't want it to pick a down action early. For example, like here, like language model says like I really want to finish, but like your affordance model thinks like maybe I shouldn't finish, something like that. And by combining these two scores together, your model would be able to get a plan that incorporates the real-world feedbacks. So how does this look in real world? If you apply this you put this on the real robot. This is done by Google folks. And you realize that I can give it very free-form language instructions, and will be able to accomplish this complicated task for you. Of course, given a predetermined set of skills that we already trained on. Okay. So here is a list of extended readings in large language model plus planning if you are interested in. But feel free to look that up after lecture. But like today, we are going to dive into we have a lot of things to look at, and we are going to dive into the next section. So the previous paper is called Secant. It's one of the first works that does large language model plus planning, but on real robots. So it still have the problem. So for example, in the vanilla Secant paper, their main point is about like real robot execution plus this large language model planning. However, in the real robot execution, the object lists are hard-coded. It hard-coded a 30 category of objects. The object locations are hard-coded. If you just move your Coke can a tiny little bit on the table, your robot stops working. It stops bringing the Coke can to you. So that's problematic. And also, it assumes that all the objects are available in the scene. This is really bad because if my robot want to look for some fruit, if it goes around the room, didn't find an apple, it should not output down. Instead, it should try to propose something alternative. Try some alternative fruit, for example, a banana, and search for a banana in the room instead. So this is really bad. Finally, I don't have perception, so it's still quite limiting. So then there came a lot of work, including one of my work on grounding this language models with visual world. For example, so some background information here is that in recent years, our vision tools are also way more powerful. So we have open vocabulary detection, where we only need to give it an object name, and we'll be able to draw a bounding box of the object, of the specified object, like giving your text prompt. So what we do here is that you just let a robot do unsupervised scene exploration in your kitchen. And while you do the scene exploration, you just try to record the location of every single object. You have an object proposal network. And then you can extract the language embeddings. So there are these models where you can associate language embedding with these objects. And you basically make a map of objects, but you can query them with nature language. You just give it an object name, for example, like a drink, and will immediately search for relevant objects, giving this text prompt, like in this map, and give you the location. So now the plan would look like this. So given instruction, recycle the code can, your robot actively use your large language model to propose some relevant objects that the task might involve. For example, here it proposed code can recycle bin. And then for each object, it would query this map and find their locations. And then it will generate executable options. Notice it's quite different from SayCan itself, because SayCan you have a predetermined list of executable options, like pick up apple. Here instead, given the object name, proposed here, it generates these executable options and try to call relevant policies here. And finally, using the same way as SayCan do planning, we can generate a plan using the generate the plan based on what's actually in the scene. So this is what it looks like. This is vanilla SayCan, in NL map. Instead, you use your map as a tool, use your vision model as a tool, and you actively propose this executable options with large language models. As a result, we will see, if you go to our website, you will see that we can have the robot accomplishing a lot of fancy tasks. For example, you can ask it to put brown multigrain chips in the woven basket. Object proposes woven basket, multigrain chips extracted from this free-form language. And this is not previously possible with SayCan because they have a relatively small set of objects. It doesn't know what a woven basket is. While in this model, you can actually call the navigation API to go there with open vocabulary instructions. You can also watch an Apple, ask it to it will propose that it should go to the sink. So there are also a lot of other awesome work, concurrent works in this field, large language model plus vision plus robotics. LM nav came first in the summer. My paper came second in domain of manipulation. Then there is VLM maps as a concurrent work. Yeah, these are all very interesting works back then. But now we all know that we have visual language models. Many of you have played with GPT-4, aka GPT-4v. Okay, so now large language models can use maps and visions. These are all useful tools for robotics. But what about using other hardwares and algorithms? For example, in many real-world tasks, given a text prompt, you might want to call some tools to accomplish a task for you. For example, here you call a calculator to calculate certain things for you. You can sometimes call Google Calendar. You can call Wikisearch to compile your answer for humans. And you really want robots to use tools as well. How do we do this? I think one important way to do so is by asking large language model to coordinate other tools by writing code. So Ross have briefly mentioned code synthesis for robotics in one of the previous lectures. So what does this look like? This is what I wrote in VS Code. I just wrote 4 functions here. Like these are like API-like things without actual implementations. You don't need to finish the entire function for large language models to use them. Instead, you just put 3 dots here and describe this function. And large language models, by looking at the name, by looking at the return behavior, like will kind of understand like what these APIs are for. And then whenever you give the language model a new instruction, for example, help me put the apple on the book, it will be able to utilize this prompted APIs to accomplish tasks. The robot will just synthesize this program for you. And after you synthesize the program, you replace your API with your actual code, actual implementation, which a large language model doesn't need. Like it just needs to know the API, and will just compile the APIs for you and write the script for you and execute the task. So that's what we do in program synthesis. So this paper, Code as Policy, is one of the it is one of the best papers in ICRA last year. It also does something like that. It calls you prompt it with a list of perception APIs. You prompt it with control APIs, and it could use this high-level APIs to synthesize a program. And however, keep in mind that you still need to give it API. A lot of dirty work is still behind the APIs, and you need to implement them yourself. You can also scale this up to non-robotic contexts, much more open world tasks. For example, like I really like playing Minecraft, and there was a growing interest in Minecraft in AI, because AI researchers, they want to do the promise of AI is solving open world tasks. I don't want to constrain my robot in a room or on a table. Instead, I want them to accomplish open world tasks like hunting the Ender Dragon or something like that. And in Minecraft research, people want your agent to learn those themselves. Turns out, me as a kid, when I first began to play Minecraft, I have completely no idea about how to craft a pickaxe, right? Instead, I go to Minecraft wiki to learn those kind of skills. It's really hard for a human to learn how to use a crafting table like without this tutorials. And it turns out, with large language model, you can compensate for that factor too. Large language models have read so many tutorials online, including Minecraft wikis, and they've also read a lot of code and synthesized code for you. And when it knows both of these two things, it will be able to generate these programs that help you play Minecraft. So if you give it a small set of skills, it will be able to like synthesize programs for more complex skills, and you can add those more complicated skills to your skill library, and so on. As a result, like you will be able to create a really, really fancy, intelligent Minecraft agent that was able to like acquire a lot of tools and acquire a lot of resources. Yeah, there has been a lot of breakthrough. If you're interested, you can feel free to read this paper as well as like the data set you use this, which is MindDojo. Okay, we just finished the first section about large language models. Great, I finished in time. And in the next section, we're going to talk about challenges and opportunities. So first of all, I realized I just walked through everything so fast. I wonder if people have any questions regarding the first section. It seems that everybody is very familiar with large language models. Okay, we have a question.
One question I have is that to what extent you still have to hard code specific commands in your robot. You mentioned that earlier that, like, for example, if the language model can pick from certain, like a stack of 30 commands, and then like if let's say swinging a broomstick, if that's not within the commands, it could never do that. So how do you connect how can you have an open-ended command wall? Does that make sense what I'm saying? Like,
Yes. That's a good question, which is exactly what I'm going to talk about in the second section. So I think a good summary of previous section is that large language models are really powerful. They can learn all the common sense information. Actually, I might have them here. Yeah. So why is large language models so useful for robotics is that first, they can parse unstructured tasks to structure programs and use all the existing tools here. The second reason is that large language model absorbs common sense knowledge. However, when I say it can connect to unstructured programs, to connect the unstructured tasks to structured programs, I'm assuming that you still have these low-level programs that your large language model can use. Your large language model can still do the very high-level things that human can tell through instructions. which is exactly going to be what we are going to talk about here, this section called challenges and opportunities. So challenges come first. So here, why is large language models so useful for robotics? So large language models absorbs common sense knowledge. However, how sufficient is this point for robotics? If you think about this, ChatGPT is really powerful. I'm using it for like all sorts of things in my daily life, and some of you like use it to write essays, and your teacher cannot differentiate it from essays written by actual students, and they're really powerful. However, if you ask ChatGPT to pick up an apple, it's something that it cannot do. So you immediately realize that what large language models absorb is that Wikipedia, books, websites, all this useful information about high-level instructions. However, text is not the whole world. Humans do so many tasks with vision, and humans also do so many tasks with their physical body. And these are both important quantities for robotics, but that large language models doesn't capture. For example, and the major question is, can we replicate the success of large language models in robotics? And I think this is one of the most important sections I'm going to cover today, because now everyone is suddenly they think robotics solved. ChatGPT is here, like we will solve robotics. Maybe robotics already solved. Researchers ask me like, oh, we already have like a robot transformer. Like, is robotics solved? Do I even need to continue in my PhD work on motion planning, right? Like, however, there are still challenges here. Like, can we replicate the success of large language models in robotics? Can we have a robot GPT? So the situation is that large language model is good only because they are trained on internet scales of text data. Is that the case for other domains? For example, vision and actions. Robotics care about actions. Even if you don't do robotics, even if you just do like Minecraft agents, like you still don't get all the actions for free. You have a lot of YouTube videos of playing Minecraft, but like you don't get the mouse, you don't get the keyboard input of those from those videos. So people have proposed this concept of multimodal large language models. That is, instead of just having a model that takes in text and output text, now instead I have a multimodal model that takes in different modality like text, vision, and action, and output text, vision, and action. So that's a dream of AGI, right? Like we humans like just have a few audio models like text, vision, action, maybe audio, like something like that. So this is a multimodal large language model people are imagining. And before we dive into how can we get actions, replicate the success of ChatGPT in robotics, having a ChatGPT for actions, we can look at the case for multimodal models in computer vision, for vision. That is visual question answering like questions. That is like I can give you an image. I can ask. We can input some text asking some question about what's in the image. Ask something like, for example, like I take a picture of the bike. I ask like, how can I fix the object in the image? And like you expect your GPT-4V like to output a set of instructions, knowing it's a bike, although you didn't tell it it's a bike in text. So that's a dream. So let's look at this, how visual language models work. For example, how many of you have played with GPT-4V? Fewer people than those who played with ChatGPT. Okay, so GPT-4V is a multimodal version of ChatGPT or GPT-4. It came like almost a year after ChatGPT. It's really late. And visual language models are GPT-4V is a type of visual language model, which is a type of multimodal model. That's a relationship. And vision language models are pre-trained on image-text pairs like this. For example, here I have an image of MIT, and this is a caption associated with that image I found online, right? So you can imagine that I can just crawl the internet and get all this paired data points of images and text. And you can pre-train a text encoder by like learning a contrastive representation of that. How many of you know contrastive learning? Okay, so basically like, okay, I think I should talk about this a little bit. So you know, like ChatGPT is a decoder-only architecture, but like if you want to let it taking taking image data, like what typically do is like you feed the image into a ConvNet or like transformer, encode the image into some low dimensional embeddings and feed into language into the large language model, and equip to combine the two modalities. So you want to make sure that image encoder it extracts information that's actually used for the downstream tasks. At least it needs to know the fine-grained information like in this image. And the way they do it is that like they throw they train the text encoder with contrastive learning. It's a representation learning method that takes in an image and it's paired text, and the model should output the likelihood that's as big as possible. And if you throw in an image with a text that's completely irrelevant to the image, you just random sample a piece of text, and should output something that has really low likelihood. So throughout this way, like you will be able to associate images with text, and people have found good performance on this, like on classification. And the lesson is that like if you do this kind of large-scale contrastive pre-training, like on this kind of internet scale of paired image text data, you will be able to learn a very good image encoder that takes an image and embeds into some low dimensional embedding that contains the semantic information of it. Is that confusing? Yeah, tip, exactly. Okay, great. We have enough time, so feel free to ask questions. Okay, so now you pre-train the vision encoders with contrastive learning, and turns out like this works really well because paired image text data is still widely available on the internet, though they are really dirty and not at a scale similar to text data alone. For example, I once saw like I was once examining a data set that collects a bunch of like paired image and text data. It's really noisy. I was crawling it from the internet, and there was like one particular data point where it's an image of like a random lake, and like the text paired with is like report, like report this like a harassment, report this as blah blah. It's just those things, nothing about a lake. So the quality of the caption here can be really bad if you just crawl them from internet. However, they are still quite, you can still get a lot of good data like from the internet. So this means that you can learn a reasonable image encoder that can like learn a good representation that helps with generalization. However, you still face this problem of distribution shift between pre-training and inference. That is, you are trained on caption. What people do is like when they train multimodal language models is that they take this pre-trained image encoder, they take this pre-trained language encoder, you concatenate them together, and you fine-tune them for the specific task of captioning. That is, you throw a multimodal model like with this image. You ask it to predict the next tokens given the context. For example, I give it this image, I give it the campus, and I hope the language, I train it to predict something like of the Massachusetts Institute of Technology. That's captioning task. However, what you actually want is like you want a multimodal model that takes an image, you ask it a question. It's not, and you ask it to like do a chain of reasoning, something like that, instead of just captioning, right? So, but those data is not plentiful on the internet. Nobody is captioning like an image like this with what I just described, like AKA question and answers. Instead, they just caption it with like what's in the image, a description of what's in the image. And when people train large multimodal models, they do this task. The main task is like captioning. And turns out this is really bad because at the test time, as I said, you want to test on question and answers and other fancy tasks instead of just captioning. So there is a distribution shift. This is unlike just a large language model. Large language model, they're trained on Wikipedia. They are trained on so many essays. They're trained on so many code. They're trained for completion. Their train time, test time behavior, the distribution is pretty similar. And that's why they work so well. And that's why GPT-4 came a bit after GPT itself. Because there is this distribution shift, and you have to ask the humans to annotate additional data to compensate for that. It's not like you can pre-train it on internet. It has this skill like out of the box. You have to ask human to annotate it. Andrew. Yeah, I think that's a good question. So if you look at GPT-3, which doesn't have a lot of intensive instruction tuning and ROHF, you realize it's good, but like it's not at a good level that it will impress you like ChatGPT. So there is a slight distribution shift. For example, like I ask it to write code, but I can ask it to like in this class we use Drake, right? And there's a reasonable amount of Drake code on the internet, but like when you write your homework, write your own project, like somehow like ChatGPT and Copilot will write code of Drake like itself, like for a task that you select, that probably nobody have done before, and somehow it extrapolates. That is, you can argue there is some distribution shift and it generalized, but I think the gap is way smaller than the train time, test time behavior of visual language models. Oh, that's a good question. So I think there are a lot of challenges in this, as you will see later in the opportunity section, right? Like generating diverse things is really hard. Generating captions, I think you have to use a lot of templates to synthesize those. And I think like you really need to put a lot of effort to make them diverse enough for generalization. Yeah. So this is a case study for multimodal for vision. And this is unlike large language models. And the takeaway is that because of these issues, you will, to get a good visual language model like GPT-4V, you will need to hire a lot of people to annotate question-answer data like about the taking two models, right? You need to annotate it. That's the point. And annotation is expensive, and we don't want it. We want to eliminate it as much as possible. So how to solve this issue? Like people do extensive instruction tuning, supervised fine-tuning. This is supervised learning, like with human annotation. And people connect the image encoder with pre-trained large language model, so it has language knowledge already. You don't train the language branch from scratch. Instead, you concatenate them. Okay, and we should look at this. So if you actually use GPT-4V, you will realize it's actually really good. It's really good, like despite all the challenges. And why is that? That's because like if you look at the input behavior here, we use pre-trained encoder for text, the pre-trained encoder for vision, and they all incorporate the useful representations already. They are trained on large-scale internet data, so they have some generalizing capability. So if you look at output behavior here, you use a pre-trained large language model, which is pre-trained to output text, right? And it works here because output is text, so we have generalization in output behavior as well. Like it's an initial pre-trained like language model. However, if you take a look at actions. So now this is a case study of actions, which is what we want for robotics. At the end, we hope a robot GPT that takes text instruction and current observation and just magically output the joint angle movements for you if you give it maybe a URDF or something like that, right? That's a dream. You want actions. So what's different here is that if you look at the encoder, it's still pre-trained. So we have some generalization here. However, here, like you want to output actions, and there is no large-scale model that's trained to output actions, at least not at the level of ChatGPT yet, because okay, your output behavior here is unclear. It's hard to get data to have a foundation model that generates actions. So that is because who annotates actions on the internet? Who writes joint angles into your Twitter post, right? You always put an image there instead of writing your joint angles. Today I moved my hand 2 degrees to eat this delicious meal. Like nobody writes that, right? You don't have action data on the internet. And turns out this is a very big problem for robotics. Like so there is even less paired action data, like despite considering the fact that the action itself is already scarce on the internet. This is completely unlike the scenario in visual language models. And here, like what you actually want is a model that generates actions as something pre-trained like that. It generalizes. You hope that you can just concatenate it with pre-trained text encoders, pre-trained vision encoders, fine-tune it, and hope it will be efficient. But there is no such thing right now. So what do people propose is that let's just try our best to collect enough data. But the promise is that like the input encoders, the image encoder, the text encoder already provides part of the generalization. So we just need a little bit of action data for the whole problem. Right? And there has been a lot of valuable scientific explorations in this direction. For example, the robot transformers from Google, RT1 and RT2, and TRI also have large behavior models. Basically, we ask human teleoperators to teleop robots, like maybe with VR, maybe with other things. Like we just collect data of like 50, 100 skills. We collect the data and annotate with them with language, and they also have images inside. And the hope is that like if we just collect enough of this data, and we can compensate for the fact that we don't have additional data, right? So TRI has been doing like this amazing work of large behavioral models. Russ is here. Russ was the leader. You can see that human teleoperators can like teleop the robot do some amazing tasks. I believe these are like after you collect the data, like the robot just learn to do it itself. Like I think this is for like a 50 to 100 tasks. And can we just collect data and achieve what we want? Oh, by the way, this is an amazing work that also comes with a talk this Thursday. Don't miss it. Like it's here. Like it happens in Stata like Thursday 4 p.m. If you are interested, definitely take a picture and don't miss it. Good question. As of the beginning, like this work is based on diffusion policy, which is trained with supervised learning per task. And right now, like what TRI is doing is why we try to combine all these things into one maybe text condition like models, and hope you could generalize. I think that's a promise of like all these models, like RT1, RT2 from Google as well. Like you put everything into a single transformer, and hope it would help it generalize better. Then the question is this enough? So the problem is that each operator still needs an expensive robot to collect your data. So for TRI, they have, if you look at the video, you will realize that the need is set up. Like you essentially have two Franca arms here and two teleop stations here, like to collect this data. There has been cheaper hardwares, but you still need to hire humans and buy them robots to collect this data. And if you ask the robotic graduate students, do they like collecting data? Do they like collecting data? Like everyone will tell you no, right? And there has been a lot of work in academia and try to do this sort of things. And the solution they have is undergraduate student descent. They just hire increasingly many undergrads to help them collect the data and hope they will solve the AGI problem for robotics. So I think this is a miserable way of thinking about things. So the lesson from ChatGPT and GPT-3 is that you need unsupervised learning, and you need plenty of data that's not directly annotated by humans. In addition, even if you can hire a lot of people to collect your data, usually like you can imagine that people do this in your corporate office or like a robot station, like in academia, and there is very limited environment task diversity. Most of us, like if you look at the Google's videos, you will realize, although it's a great science exploration, I would say like they still focus on like tasks like pick and place. For example, I remember like it's in RTX or RT2, they have tasks like putting an apple on Taylor Swift. Like they just have a photo of Taylor Swift and other people like on the table, and the other robot to put the apple on Taylor Swift. So you can see this kind of generalization is weird. Like it's still pick and place. It's just pick and place to like to weird like destinations, right? So if you ask that model like to actually I don't know, like bake a cake for you, you actually need to collect a lot of data about baking cakes. It will not generalize like without those annotations. So therefore, like we really have a limited environment and task diversity. And this approach shows some generalization in individual tasks. For example, like as I mentioned here, like after you collect a lot of data like about like a certain task, like for example making a pancake. At test time, like like the pancake maybe is at a different position, or your tool have like slipped in your hand. The robot is still able to generalize, but only at the level of like pretty much the same task. Maybe you change a table, it will fail. Maybe sometimes you use pre-trained video encoder, it will generalize to different tables, but it's still like if you train it on making pancakes, it only knows to make pancakes. Like to actually like reach a level of like a robot GPT, I imagine you will need billions of tasks collected, and then it will work. And I think it might scale up. So if you ask me like, will this thing, will robot learning scale up? Will imitation learning scale up? My answer is that I think the architecture and models are there, but the question you want to ask is data. Does the data scale up? I think the model scale up, data doesn't necessarily scale up if you just ask human to collect data for you. Okay, so robot GPT will need way more and maybe internet scale data containing actions. It's very frustrating to think about this, right? I just hope everyone, like when they post the nice photos on Instagrams about eating food, they'll just post their joint angles and movements as well. And suddenly I can have enough data to train my robots, right? However, it's not possible. Let's admit that we have very limited action data on the internet, at least action data in Lagrangian states like joint angles. However, we do have a lot of other ways of extracting action data with foundation models. This is some alternative approaches, some alternative opportunities, which makes me still super optimistic about the future of embodied AI and general purpose robots. And we'll see some of them here. For example, this paper from our lab, from Li Rui, who is not here, he is using large language models to generate generate robot simulations. Like with a certain amount of assets, they just ask large language models to synthesize code for physical simulations. You can see that each of these tasks is associated with some language prompt, and like it just generates it for you. So in addition, this is another work that generates simulation with large language models. On the other hand, like generative AI is really powerful nowadays. If we can generate images, like using DALL-E or this kind of models, we can also generate 3D, right? There are so many good startups about generating 3D assets just from text prompt or a single image. And I expect there was a huge boom in 3D assets in the future. We will have this huge set of like text paired 3D assets that you can use for simulation. And then in the future, like you just have use this generated models, you'll be able to generate simulations containing robots. And maybe, as promised by like many reinforcement learning researchers, once you have like this kind of simulation, you just train your robot into them, and you can get actions from reinforcement learning, right? So one step further to that, like I just talked about reinforcement learning, and we've learned about reinforcement learning in this class. And one important component of reinforcement learning is you need to have rewards. It turns out people don't do reinforcement learning in real life very often because it's just so hard to get a reward, right? Even when you want to just pick up an apple, you really want to have pre-trained vision models that tells you how far you are from the apple. You also want the model that tells you like if the apple is already tightly gripped by my hand, right? So it's very hard to annotate rewards. However, with foundational models, it actually becomes possible. For example, in these two papers, my friend at Google had used large language model to annotate rewards for this legged robot, this robot dog. And from NVIDIA, Jim Fan and his team have this paper of like using large language model to design reward functions. This is just design reward functions. However, like now with we have GPT-4V on all these visual language models, and people start to use them to actually like annotate rewards by directly question GPT-4V, or I think this is with Flamingo. And you just show it images, and you ask or videos, you just use these visual language models, ask them like if I already have my apple in hand, or like or something like that, yeah. And you can ask them to annotate a reward. So there's all the opportunities here. So imagine all of these things like work so great, and you have unlimited amount of compute. Right? You can generate unlimited amount of 3D things where you can throw unlimited amount of robots in your simulation and train for unlimited amount of years with unlimited like diversity of reward annotations, like this task. And the promise is that with all of this, with all the foundational models, you will get a promising thing from like action data and policies from just generated data. So on the other hand, people also have used, this is from my friend Wenlong at Stanford. He used foundation model to write code to generate a cost function for motion planning. So everybody here have learned about motion planning. We just generate code that specifies the things, and like we can render 3D cost map, and then use motion planning to achieve the task, to achieve the lowest cost here. So with all of this, we have foundation model to simulations, foundation model to reward and cost. Maybe we can generate internet scale action data with enough compute. I think that's a good promise of this thing, and I would actively encourage everyone to explore these opportunities. I think there are a lot of things we can do, like with all these foundation models all of a sudden. So before we dive into the next section, yeah, questions? Oh, it's physical. Yes. Yes, exactly. Yeah, good question. LLM, there has been a lot of like simulation, like code and documentation from internet. For example, for Drake, for Pipelate, right? Like it already knows a lot of like programming with these two boxes, which simulation frameworks, and they could write viable simulation code. Large language model have also seen a lot of URDF files on the internet. You can actually ask it to generate URDF files. And Leray here, I do think he fine-tuned the language model a little bit to make sure it's better. But after he fine-tuned with Laura, like the language model just output the code for him. Exactly. Yeah, it's still like it's an advanced way of doing tool use. It's using a simulation package library as a tool, right? It's not like really predicting this frame by frame. Like it's not generating a interactive simulator for you. Yes. Any other questions? Yeah, I believe it's somewhat like like code for the simulation environment. I don't know how many of you have played with like Gym or Drake Gym, OpenAI Gym. Have any of you? Like like you write some code, you write like robot hand move to blah blah position as an action, like get action function, right? Like something like that. Your large language model also outputs code here, outputs your Drake code out to the code for manipulation station here. Your large language model can also help you create URDFs out of the box. That's another thing, right? So the fun story is that like I was trying GPT-4V with my undergrad student like a few weeks ago. I just take a photo of the fridge, actual fridge, like in our lab, and ask it like, can you express this like in like what links are there on this fridge? Tell me like are each of them revolute or prismatic? And GPT-4V is able to give me that, and then you can imagine that we can use the large language models to generate corresponding URDF files for this. Like I was working on a project like this. It's really powerful. Other questions? Okay, great. So before I dive into the video prediction section, I do want to note that like there are a lot of AI foundational models nowadays. In particular, people propose the concept AIGC, right? AI generated content. And I think every single of them is useful for robotics. If you generate images, it's good, like as you will see later in my later video. If you generate text, it's useful, as we saw in planning. If you generate 3D assets, it's used for simulation, right? Like almost every single of them will contribute to the great development in robotics. So in the last section, I'm going to talk about video foundation models. Previously, we've talked about ChatGPT and those text foundation models. They're trained on internet scale text data, and there's so much data that like once you instruct into them a little bit, they are so useful for many diverse downstream tasks. However, as I also just said in the opportunities and challenges section, text isn't the whole story. There are so many tasks that we humans learn that cannot be described by task, right? In fact, if you look at the number of bits for a text file and the image file or video file, you will realize image files are usually much bigger because they have to contain way more information than just text. And if you just use text, there's so much information to lose for you. So in this section, I'm going to talk about video foundation model. I call it a word model for embodied agents, and I will explain why do you need that. So why do we need video? First, video is how humans perceive the world. Humans perceive all its physics and all the 3D world via just vision, right? Like right now, like people have like technologies like nerves, Gaussian splatting, this kind of technology. You just upload a video of you walking around like a certain objects, and like it will give you a 3D objects. That's possible because video is very foundational. It's how we humans perceive and like get structures about 3D world. My object is loading here. Let's see. Let's go back. Video is also widely available on the internet. How many of you have uploaded a video on TikTok on YouTube? How many of you haven't? Have never uploaded a video to the internet? Okay, we only have one student here. Like all of you are contributing to the future of robotics by just posting random stuff on TikTok. They're so widely available on the internet, and when you actually take videos of yourself and other people, some of them are useless, but many of them contain your actions, and those are still super important. And finally, internet videos contains human actions and tutorials. It's not directly in the Lagrangian actions, but there are many dedicated videos on the internet that contains instruction about how to do things. So this is not loading, so I'm skipping this slide. But this is basically, with this app, Luma, it's from Berkeley, from a startup from Berkeley, Bay Area. And like what I did here is I use the app I uploaded a random video I took of a bottle, uploaded to the app, and it would give me a very good 3D reconstruction of it. Nothing else needed. So there are a lot of videos on the internet. For example, like during COVID, YouTube celebrates this event when Minecraft had 1 trillion views, right? And you can see, and in fact, a lot of best AI researchers I know who are interested in body AI are also Minecraft fans. They watch a lot of YouTube, like Technoblade or Dream, like during the COVID, and watch a lot of YouTube tutorials. And in fact, if you go to action tutorials, you can learn how to make egg fried rice. You can learn about how to do Minecraft PvP or survival by watching tutorials. That's how we humans do things. So the promise of video production is that you just have a vision foundation model that's trained on entire YouTube or some other high quality data subset, right? Or maybe on movies or something like that. You train on entire YouTube. That's unlimited amount, almost unlimited amount of data. And then you train a model such that it can generate a video from first image as well as text prompt. You know, like YouTube have like this subtitles, right? You click subtitles, and many of them would give you the English subtitles, the text conditioning you need. And you can use them to train a video. There's a lot of data. Like, and then after you train this foundation video model, you fine-tune that foundation video model on some robotics video. It doesn't need to be a lot, right? Just like as I saw like earlier, like in text, in future prompting of large language models, maybe you can prompt a video model with a video of your robot completion task, and then it will learn that like when you give a new frame or a new robot, like it will accomplish tasks based on your text input. Right? You imagine that because it's trained on so many YouTube videos, it can know the structures about like my hand shouldn't disappear midway, right? When my hand like reaches the laptop, like some fingers disappear from my viewpoint, right? It learns so many, absorbs so many information that when you fine tune it, it doesn't need that much data. And in fact, even if you need a lot of data, if you just put a camera on humans and put a camera like around the robots and humans collect, I think it's still way easier to set up than the case where you also need to collect egocentric views as well as like the joints. You know, like when I collect imitation learning data, if I collect it with Franca, I don't expect it to transfer zero shot to KUKA robots, right? Or if you collect with videos, like you can expect that video data collected on one robot may still be useful for another type of robot morphology. And finally, like after you fine-tune some robot video at inference time, given an observation image, my current observation, for example, pick up an apple, right? And the text prompt of like, I don't know, like pick up an apple. Like, and they will this foundation model will generate a video of the robot actually performing the task. And for example, it will generate a video of like your robot hand like picking up the apple. And after that, you can do something to back out the actions. So this is not directly predicting the Lagrangian actions, but this is one of the fundamental ways about how we humans acquire new skills by watching others' videos. And we can probably back out actions through this. And I really like the line of Izun's work, which I'm going to mainly focus on in this section. So Izun and Sherry, like from DeepMind, they created this foundational universal dynamics model that is trained on like all sorts of videos online. I believe is it trained on image and video from Google? I don't know. But like basically like when you train on huge amount of videos, it generalizes so well. Like it will generalize. There are a lot of startups doing video prediction nowadays, and I expect it to get really good. Like for example, here, like if you show it like a few frames of me dropping an apple, like it will actually like impede the trajectory of the apple dropping to the ground. And those videos are sometimes so realistic that I can't tell they are generated or not. I think that's really promising. And in his work of this is universal policy or UniPy, what he implemented is exactly this promise. So we pre-train on large-scale YouTube data, we fine-tune on some robot data, and the inference time, given observation image, plus some like other conditioning, you generate a robot video. You will be quite amazed that all of these frames here, like here, are generated. They're quite realistic, right? If I don't tell you, like, if you don't look closely, even if I look closely, I will find them still super realistic. Like you'll see, like, it just flips this this part like very well, and then like you can expect it after we generate this, you probably segment this thing out. Like they use an inverse dynamics model, but there are other ways to do this. You can detect auto flow combined with the depths, back out the movements. It's still hard, like it's still hard, but I think this is just really cool because it gives us actions out of nowhere just from YouTube data. Yeah, no, not exactly. So when I say inverse dynamics model, so you remember they fine-tune this on some robot data, right? So those robot data like not only contain like just videos, like they also sometimes when you collect trajectories, they also contain actions. So what they have is that they train a model that takes in frame t and frame t plus 1 and predicted the action at. The action. Yeah, Lagrangian actions. That takes you from observation frame t to frame t plus 1. That's what I'm by inverse dynamics model. Yes, that's true. But you can imagine that it's way easier because if you just segment out the robot hand, right? Like you can imagine, like it's easier for me to collect like a data of just a robot hand, like moving around like to every single possible pose before a green screen, right? And you can so the diversity is way less for the robot hand itself, and I expect to generalize reasonably well. Yes, that's true. Like you also need to do that, yeah. but this is not a unique way to do this. Like if you only care about like an anti-factor space control, if you workspace control, or you can also use if you have depth camera and you can have like some state-of-the-art optical flow estimation methods. Maybe you can directly back out the scene flow. That is like the 3D movement just from 2 frames, just from computer vision, right? It's in Euclidean space, and because you back this out, you can use any workspace control to steer your hand like to follow the action. I think that's exactly what some people have been doing, right? It's just that like people's choice of like the intermediate abstraction is any factor position, right? The low level, it doesn't predict the joints. Like people predict the delta movement of any factor and use inverse kinematics to like plan the trajectory. Good question. So it seems that force is really hard to extract from videos. And I guess like for those scenarios, you do need to collect some data. In fact, Russ and like the TRI, the hardworking TRI folks, told me that a lot of tasks they had in the large behavioral model requires force feedback. But those tasks are like, many of them are like, they're deliberately chosen to need force feedback. There are still a lot of tasks in real world that doesn't need force feedback. And I think what people want here is like, I try to solve 80% of tasks first. That's better than solving nothing. Yeah, while the 20% maybe they are the like a crown jewel of the robotics problem at the end after 100 years, and but like eventually you just have generations of undergrad collecting data for you, and you will solve it. Yeah. Any other questions? Yeah, that's a topic of great debate. In fact, in choral conferences here, like we have this giant debate, like Ross with actually with Sergey and Chelsea, like debates with some other folks. Ross before the debate, Ross said he's fine being on the other side. Ross sees the whole picture, right? But like there is this big debate about like, is scaling up all you need? Well, we have a learning-based policy at the end. So I think like at the end, like it seems that like transformer and learning are surprisingly good at amortizing things. So it is like if you look at autonomous driving nowadays, which is one of the closely related field to robotics itself. Autonomous driving people, like they right now they still use a lot of trajectory planning with LiDAR, very structured methods, like to control their cars, make sure they are safe. But if I collect data for like 100 years, after that I just collect enough data, and maybe if I just throw a transformer at it, and it will just like drive the car just fine, like from pure vision. You don't need LiDAR, you don't need like any structured methods at all. So I think like right now I'm only talking about that one plausible way of solving robotics after 100 years. That is, once you have enough data, maybe you just amortize the transformer. However, as I've been emphasizing in the second session, data is important. And I do think that structure, because robotics is so different from language, it doesn't have data, right? And I do think like this kind of structure is super important to generate robot data. And maybe you still need like a lot of like planning to generate this data. Like in addition, even after you use a video model, right? You back out the delta movement my hand is supposed to move. You still need like controllers like inverse kinematics. You also want like a planning method to avoid collision, right? So I think all of this will contribute to the robotics field of robotics eventually. But if you're asking me from a learning perspective, I would say models, transformers, have a good likelihood of scaling up. But for robotics, data doesn't right now. And that's a problem that all of us need to think about.
Talk a little bit about how you make sure that these probabilistic approaches are safe and don't do anything crazy like swinging out an artifact or something.
Okay, that's also a good question. So a lot of people in robotics are focusing on safety and safety guarantees. So I can say like safety and provable guarantee are two separate things, right? If you use neural networks, it's very hard to prove that they're safe, right? Unless you have like some hard-coded like a high level decision trees that make sure like your car like stays on the lanes, and like if they don't fail at all, like they will serve as good like failure detectors and guarantee you are safe. However, like I think from the algorithm side, although we cannot prove that these robots are absolutely safe, many of the design choices here make sure they are like they're reasonably safe. For example, if you go to look at diffusion policy and the large behavior models, they are trained on diffusion models, which is like at training time you add noise to the data you want to predict, and I ask it to output things, right? So if those data are explicitly augmented with noise, some of which being like somewhat like numerically unstable because you sample from Gaussian, and Gaussian can be really have some probability of getting numerical properties, but they're explicitly trained to stay in distribution by mapping the thing to the original data, like by the training of diffusion policies themselves. So I actually think like with modern approaches, you can get a reasonable guarantee that these things will stay away from unexpected behaviors. Like if you asked me like 3 years ago, I might say something different because back then like some people work on reinforcement learning, or like you just have a learned dynamics model, learned reward model. You do gradient descent to back out the desired state and action. You hope that like it will give you high reward. But your learned model can be inaccurate, and when you do something like that, you will exploit the inaccuracy of the model. Sometimes in reinforcement learning, during my undergrad, I was training some robot tanks playing FPS games with each other, and we realized that I was using RL, and I realized our model just exploits the bug of the simulator all the time to achieve high rewards, and this is an undesirable property, right? But I do think like the approaches nowadays, like diffusion policy, they empirically, and also like just from the design principle, they seem to have better behavior in terms of making sure the actions stay in distribution. Other questions? This is another video from UniPy. You can see that these are like also very complicated things. I just give a text prompt of like put detergent from sink into drying rack, like something like this, right? You will see like this generalized to this scenario. Although I have to say, what I heard is that like we still haven't collected enough robot data such that we have a foundation model, we fine tune a little bit, and we'll get all sorts of amazing generalization we want. Like this paper, as one of the first few works that explores this direction, still has its generalization limitations. But hopefully in the future, once we have such a huge video foundation model, maybe you just need to prompt it just like a language model. Okay. In fact, you can combine video foundation models, language foundation models. In fact, like I don't know if many of you realize, text conditioning is one of the most important reasons why image generative models work. So if you imagine that like you're generating a random picture of like you're asking your generative model to just generate a fancy picture for you. The distribution is actually really complicated. It's so high dimensional. It's so multimodal, right? But if you tell it, I want to generate a picture of a cute panda, like what will be the average color? What will be the color pattern like for the image? You will have a black and white image and maybe some green in the background, right? You have this thing in your mind. And this just means that text conditioning simplify your generation modality so much that it makes generation so much easier. And turns out, I think that will be the case for video generation as well. You want text conditioning. And turns out, you can get text conditioning for free because there are captions on YouTube, and there is large language model. You just give it a high-level instruction that says like, I think this is asking the robot to make this toys into a line, right? And it will just your VLM can output a sequence of high-level action in terms of text. And then after you have this text plans, You just condition on this image and each text, you simplify the distribution by quite a bit, and you generate a video and you back out the action. So this is what they do in video language planning. This is also a cooperation with Google DeepMind. I think it's also super exciting. So this is what I do. I didn't put the video here. Okay, so make a line. Large language, visual language model makes all these instructions with visual feedback, and I generate videos. And from videos, I just like calculate the movement of this thing and like move this along the XY axis. So I think this is super exciting. So there are also other work. This is not a foundational model, but I really like this work. So this is a model-based reinforcement learning paper. This is called Dreamer v3. So this is a model-based reinforcement learning framework, but that's designed to tackle multitask and tackle complicated scenarios from pixels. So Dreamer v1 was a state-of-art like model-based IO framework from pixels back then. And it works so well. And the important part of it is variational inference and video generation. You can use it to generate videos as well, right? Dynamics model can be characterized by videos. And here, Dreamer v3 just scale it up like all sorts of environments, even on Minecraft. You can imagine that if I have a foundational dynamics model, I can combine them with language to reward methods, all those kind of things. You use video as a simulator, right? Your video predictor always predicts the next frame for you. Your reward function, VOM, okay, VOM is also conditional on video frame. Everything is conditional on video frame. And suddenly it seems that you have a imaginary simulator using videos, and if you have enough compute, you can expect intelligent behaviors to emerge from this kind of things. So I think it's super exciting. Once we have a vision foundational model, I think a lot of embodied AI's core issues will be significantly improved. I think maybe we'll have a robot GPT in the future in terms of video foundational model. Okay, this is the last slide, and we still have 8 minutes. So the models up till like this point, they're just generating videos. Yeah. Good question. You can always do that. In fact, the large behavior model did that, like TRI, and it's important. However, I talk about video here with the promise that you have it widely available on the internet, and that's one of the most important things here. Nothing is perfect because you don't upload your joint angle on Instagram, right? That's really bad. And video is the best we can have. So we are trying to solve problems that only need this kind of high-level things. Not touch. Any other questions? Andrew? Yes, exactly. Yes, exactly. Dreamer v3, like you still use like a learn like a reward function. You still need reward annotations, but in the future of AGI, maybe you just need to use language to reward technique, VOMs as a reward annotator to finish the whole picture. So in this, like the action have to be, I think like the actions as this games or like robots taking. Yeah, you still need low-level actions here, but like the promise is that like your model have embedded so many physics inside it that like you just need to. Yeah. This is something you can train, right? And you can utilize on any task. You just fine-tune a little bit on tiny amount of action data in each domain, and it will suddenly work. yeah, if you don't have other questions, or like if you are just too shy, like I will stay here after the lecture. Feel free to ask me questions. Yeah, and at the end, I would encourage everyone to look into this exciting domain of robotics, but also keep in mind that like I think prompting robotics is a very hard problem. As I told everyone, large language model is exciting, but it only solves the easier side of robotics. And I also hope everyone here in the future, you will also tackle the hard problems, not just prompting a large language model and claim you solve robotics. Right? We want to actually solve the robotics, not robotics in disguise. I think it's a super exciting direction. I hope everyone enjoys the lecture. And feel free to give me feedbacks on Piazza. Yeah. Oh, do we have another question? Okay, thank you, everyone.